Okay, I think we can start.
Start now? Okay. Do you want to give people a few minutes, Lale, or should we just go ahead?
I think we should go ahead because we don't have that much time for a lot of presentations.
Okay, excellent. Thank you. Alrighty. Good morning, good morning. My name is Chris Runyon, and I, along with Lale Coronel, will be the chair of the session titled Psychometric Innovations and Advances in Medical Educational Assessments. Today, we have a set of 5 exciting talks that present the use of interesting methodologies to improve many aspects of high-stakes assessments for medical licensure. The talks range from the use of cutting-edge machine learning techniques to the application of more traditional methodologies to unique data structures, and they all involve natural language processing in some way or another. So just a few clerical notes before we begin. There's 5 talks to the session. We've slightly reordered the presentations as the last 3 talks build on each other with the information. Each presenter will talk for about 10 to 12 minutes, and then we're going to allow for a few brief questions after each presentation. And then following the last Q&A after my presentation at the end, Dr. Isaac Bahar has kindly volunteered to provide some perspective on the collection of talks. And if there's any time after his comments, we'll gladly entertain more questions. We're kicking off this session with Peter Baldwin, who's going to talk about the use of NLP for distractor generation. And Peter, you can start whenever you're ready.
Okay. Hopefully everyone can see that. Thanks, Chris, and thanks everyone for tuning in. Let me start by thanking Lale and Chris for organizing this session, and Isaac for agreeing to be discussing. My name is Peter. I'm going to be talking about some work I've been doing with my colleagues Victoria, Janet, and Brian from NBME, and on from the University of Wolverhampton. All right. This is a sample item. I don't expect anyone to read it. I just wanted to put this up there to give you a sense of the kind of items we write, and also to make the observation that our items tend to have a great deal of text. Now, so we've been looking into automatically generating distractor suggestions. The idea here is that these suggestions might help item writers with this aspect of the item writing task. It's been our experience, and I think it's widely understood, that coming up with attractive distractors is challenging. Nevertheless, it's crucial that we rise to this challenge if we want to prevent examinees who lack the necessary knowledge from responding correctly on some other basis. Okay, in the interest of time, let's jump right in. Let's imagine our item writers working hard to create new items, like the one we just saw. They write a new stem, they write the answer. Now they need distractors and they are stuck. They turn to us for help. These are not proud people. They plead with us. Can't we just come up with a few suggestions to help them get the ball rolling? So let's suppose we want to help them. Where would we start? Well, maybe we have some items in our bank that measure similar concepts to the stems and answers they've written. And maybe our item writers would find some of the options from these bank items helpful. And that simple idea is what I'm going to be talking about today. All right, so let's call these bank options distractor candidates. Now, in many cases, this list might be quite long. It may even contain thousands of candidates. So this raises the question of how are we going to figure out which suggestions to give to our item writers? Which ones do we expect to be most useful? To accomplish this, we built a model using 5 simple attributes of each candidate to predict its utility. Let me go over these attributes. Suppose we want to predict the usefulness of option 1.1. Well, what can we say about this option that might give us a clue about its utility? Well, first off, does our answer exactly match any of the other options? We might imagine that any set of options that includes our answer might contain other options that would make good distractors. Similarly, instead of exact matches, we can look at the similarity between each of the candidate's fellow options and the key. Next, how similar is the candidate stem to our new stem? We might expect that items involving similar concepts might be more likely to share common options. Likewise, we can look at the similarity between the candidate and our new item's key. And finally, we can count how many times our candidate appears in the entire list of candidates. If lots of items use our candidate as an option, our new item might use it too. Okay. Now for any given stem and key, we've identified a way to calculate 5 potentially informative attributes associated with a given candidate. This means it's time to build a model. So let's set aside new items for the moment and focus only on our item bank, which will be used for model building. Just as with new in-progress items, for each item in our bank, we can create a list of candidates. Likewise, for each of these candidates, we can calculate its 5 attributes. Now, since these items are banked, they already have a set of proven distractors. We then can compare these distractors to a given candidate, and if our candidate matches one of them, we know that at least some item writer out there thought this particular candidate was a pretty good distractor for this item. We can do this for all of our banked items, and then regress this match status onto our 5 attributes. The result is a logistic regression model. Now, if we come along with a new stem and key and identify a list of candidates, we can use this model to rank order these candidates with respect to their estimated plausibility. So that's the basic idea. Let's see how it worked. Data were from one of the USMLE exams. This is a high-stakes exam sequence physicians must pass for licensure in the US. We ran parallel analyses on 2 mutually exclusive sets of items grouped by content subarea. Today, I'm only going to be talking about the results from the behavioral health content subarea. Results from this content subarea were a little better than from the cardiology subarea. Lots of potential reasons for this. One of the reasons could be that many of the concepts, like diagnoses, for example, must be expressed using very specific terminology outlined in the DSM-5. This means that many of the item options use identical language, which minimizes the occasions wherein a given concept is expressed twice, but is mistakenly found to be dissimilar simply because of differences in the way it was expressed. We actually do this sort of thing in general, but the DSM-5 requires more rigor than some other content areas. For this study, all similarity measures were cosine similarities. Our corpora were based on the item bank itself. A TF-IDF vector was created for each option or stem, and distance was computed in the typical way, as shown here. Okay, to evaluate the approach, we used a 10-fold cross-validation, and this gave us an ordered list of candidates for each item in our bank. Okay, we then conducted 2 studies. In the first, we looked at which candidates on each item's list were actual distractors for that item. In other words, was our process, in fact, able to recover the actual distractors that had been written for the items in our bank? This is by no means a perfect measure of effectiveness, because some candidates might make excellent distractors. It's just that the original item writer failed to think of them. Or a given candidate might express the same concept as an actual distractor, perhaps express it even better than the actual distractor does. But since it's not an exact match, it won't be identified as a recovered distractor. In any case, looking at recovered distractors provides a very interpretable lower bound of success. Okay, in the second study, we presented 10 experienced item writers with a set of stems and keys. And for each stem key combination, they were shown a subset of candidates from among the top 50 most plausible candidates for that stem key combination. We then asked them, how helpful is each suggestion for writing a distractor? They answered this question by categorizing each candidate into one of 4 categories: not helpful off topic, not helpful on topic, somewhat helpful, and very helpful. Okay, returning to study 1. Here we can see the proportion of items with at least one candidate exactly matching one of the item's actual distractors. These are the light gray histobars. Or with at least 2 exact matches, these are the dark gray histobars. On the horizontal axis, we have the number of candidates. So let's just walk through one example to see how this works. If we focus on only the histobars above the number 3, we see that for 70% of the items, at least one of their actual distractors appeared among their top 3 candidates. Likewise, about 35% of the items had 2 actual distractors among their top 3 candidates. So that seems quite successful overall. Okay, moving on to study 2. Here we have our 4 rating categories. As mentioned, not helpful off topic, not helpful on topic, somewhat helpful, and very helpful. All the candidates that were shown were put into 2 classes: among the top 10 most plausible, or not among the top 10. Or in other words, we created 2 plausibility classes: more plausible and less plausible. Shown here are proportions within class, and we can see that more plausible candidates are more likely to be judged helpful than less plausible ones. And further, that less plausible candidates were more likely to be judged unhelpful than more plausible ones. We can also formally test whether or not panelists categorized candidates differently depending on whether they were more or less plausible. The probabilities for these tests are shown above the histobars. And we can see that in this case, we would reject the null hypothesis that plausibility class doesn't affect rating for all categories. All right, so what did we learn? Well, we found that our item bank contains distractor candidates that item writers find helpful, and that using a simple model, we can identify some of the more helpful ones. There are, of course, many limitations here. For example, we don't know how well this approach would generalize to other content domains, or to smaller, or for that matter, larger item banks. We also don't know how helpful these candidates would be during actual item writing. We only know that the item writers who participated in our study believed that the suggestions would be helpful. Finally, and this is somewhat anecdotal based on some survey responses and a discussion that followed the judgment exercise we had with the item writers, there seemed to be a sentiment that the helpful candidates tended to be some of the easier distractors to write. For this reason, these suggestions might be more helpful for novice item writers than for expert item writers. So that's something to think about in future research. And I think that's it. Thanks for listening.
Thank you very much, Peter. There are no questions in the chat so far. So if anyone has a question for Peter, please post it in the chat room. I do have a question actually in the meantime. So this interesting tool that you presented, that you use for using old distractors to create new items, are they, is this tool consistently updated as new items are developed?
It could be. I mean, it's just, we actually have, so this research is based on just sort of crunching the numbers, but we built a little app for item writers to actually write items in. And that uses, that sort of builds the model and uses a set of items to build the model and to generate the list of options to begin with. It could be updated. It takes a little number crunching to update it because it's just a big model. The software does do something though that we didn't talk about here, which is it updates the list of suggestions as you write new distractors. So we have been working on refining it, but we don't update the bank itself on the fly at the moment.
Okay, I see. Thank you, Peter. And as there are no other questions, I think we can move on to the next talk.
Thank you.
Kang, we cannot hear you. I think your audio is not working. Are you calling in? No, we have a very bad audio from you, Kang. There is no. I think it might be best if Chris jumps in and presents.
Sure, I'll give this a shot.
Sorry, Kang. Actually, just an explanation for the audience. Kang has a very bad reception where he is right now.
His power's out, actually.
I'm conscious. We'll talk about the research work last summer as a research intern. Already, you cannot hear me?
We cannot hear you, Kang, so Chris will present.
I'll just do my best.
But please, Kang will stay on the line to respond to questions in the chat.
Is that okay right now?
Sure. Yeah. If that's fine with everybody else, I'll go ahead and just try to do my best. And then that way, if there's...
Oh, sorry, Chris, did we just want to move Kang to the end? And hopefully he can get things worked out and the rest of us can just move up a spot?
I think we'll just, he's out of power. So it's not,
I think we just move on.
Yeah, I think I'll just try to do my best with the research since I am one of the co-authors. Yeah. So I'll just go ahead and I'll present this as best as I can for everybody. I will give the initial caveat that I am not the full expert in this. You'll have to defer any challenging questions. You'll need to email Kang and let him know after the talk. But I'll do my best to represent this work make sure that it's well represented. All right. So this talk is on the utility of using transfer learning to predict item characteristics. This work was done by Kang, who is now at NWEA, and he did this when he worked with us at NBME, and Victoria Yaneva is our other co-author. So we're going to introduce the research questions, and then I'll do my best to represent the background and experimental framework that Kang had used, and then I'll briefly go over the results for everybody. So we had three main research questions that motivated this work. One is can we use the natural language processing to extract features from item text to predict the p-value and timing of new items before pre-testing? So this is the p-value, the difficulty value that is traditionally used in CTT. Can transfer learning help to predict p-value and timing better than predicting each variable individually? So these two these two statistics have a correlation of 0.37, which means there's a moderate relationship between them. So when you're using the transfer learning technique is if the variables are related, then that means that you can probably predict one of the variables better because you're using information from the other prediction. And then 3 is deep learning based NLP method better than the traditional NLP approach. And I'll go into that in a little more detail in Kang's slides here. So just an overall of natural language processing. So natural language processing is an area of computer science that's focused on developing programs to process and analyze, understand human language. And what was important in this research was word embedding is the process of converting text into numbers. There's many different methods for creating word embeddings, meaning there can be different numerical representations of the same text. So some of the traditional word embeddings that we're going to talk about in this are just a frequency-based embedding, such as just count vectors, and other more simple analysis of the text. And then there's deep learning based NLP word embeddings. And this is a prediction word embedding. And this is when you're using such corpus and methods as the word to vector and then the ELMO methodology. So here's the relationship between AI, machine learning, and deep learning. As you see here, the machine learning is a subset of AI and deep learning is a subset of machine learning here. And why we thought it might be interesting to use deep learning for this type of analysis is that machine learning depends on some sort of human to do some feature extraction. So there is a kind of a supervised identification of what information is going to be most important in the predictive model. And then from there, you can enter that information to a simple neural network and get some classification or clustering. But by using the deep is you allow the methodology you use to identify what the important features are. And it may reveal some features that don't come to the person's mind, or may just be really kind of opaque to get at, like higher order interactions or nonlinear relationships and things of that matter. So transfer learning, this is a key part of the research here. It's a machine learning method where a model developed for a task, the auxiliary task, is reused as the starting point for a model on the second task. So to revisit earlier when I said we're looking at predicting the p-values and the timing, one of those is going to be used as the auxiliary task, and then the model that's used to predict that information is used as the starting point for the model on the secondary task. So for instance, if we were going to be predicting p-value first, we take the model that was developed to predict p-value and we use that as the starting point as the model to predict the timing for one of the items here. And using this transfer learning has 3 advantages here. First is you have a higher starting point in performance. You have a higher slope, which means you make faster gains when you're trying to learn and teach in the model. And you usually have a higher asymptote. That means you can really leverage the information that was learned in the auxiliary task. So here's the model framework here that King used in the research. There's a lot of pre-processing that went on. We used the raw item text from a bunch of our multiple choice questions here. We used both the questions and all of the distractors, the responses there. And then we went through and we did pre-processings, and in doing so, we pulled out some of the embedding features, the word embeddings, that was through the ELMO process there. And then there's also an encoding layer that he extracted there. And after you pull out all this information through the deep learning module, then you can use that and put it into like a machine learning model to try to predict the p-values of the durations here. And I did not do the work that King has done justice here, so I do apologize, but you will have to follow up with him to get some of that information. So in this experimental design, we had a total of 36 conditions when crossed. We wanted to see what worked best when we used as input data the item stem. The response options are all item content. We used 2 transfer learning methods here. Transfer learning 1 was, if I remember correctly, where we just used some of the basic elements here, the traditional NLP word embeddings, those types of things here. And transfer learning 2 was kind of this deep learning based NLP word embedding. So it's comparing how well the performance of those 2 models work together. The size of the ELMO here, there can be a lot of parameters in the ELMO models. So you can either have the original model, which is kind of running the full way that it's expected to be run. That's really computationally taxing, and we don't have so much computing power in NVMe, even though we do have some GPUs and some offline servers for these processes. And then you can see if reducing the ELMO size has any effect on performance. For the ELMO parameters, you can kind of have the hyper tuning for some of the smaller size ELMOs. But we're unable to do that for the larger ELMO just because there are so many parameters in that data. So what you have to do is you train the model to a certain point, and then you have to freeze the parameters where they are in order for the process to continue to work, just because we don't have the computational space in order to continue to work. We also wanted to see if it was necessary to use the full data set, because we understand that maybe not all persons are going to have access to the repository of items and database that we have. And with the number of samples that we do. So we wanted to see if this methodology would still work if you were working with a smaller data set or with a smaller instance at a different company. So the first finding, the transfer learning 2 method worked better for the p-value prediction, but the transfer learning 1 method worked better for the timing prediction. So the deep learning method worked better for trying to predict item difficulty, whereas the more simplified method worked better for actually doing the timing here. And here's just a quick comparison to kind of illustrate that finding here. As you can see, for half of these, when we had the original reading with the large ELMO model, there was no difference to see between the 2 types of transfer learning and p-value prediction. But here in the small tuning, both the embedding and the encoding methods worked better. And then in the middle tuning, the encoding method worked better. You see similar information here. Actually, it looks like, and for the original freezing method, the embedding didn't work any worse there, but it was worse for the other 5 conditions. The second finding, the encoding features work better than embedding features in most cases, and that timing prediction requires more abstract information than p-value information. So similar information here to support that finding. As you can see better here, for the original freezing method, 75% of the time using the encoding worked better than using the embeddings. And then here, this is a little more illustrative, that you can see that the embedding features worked more when you were able to tune the model more for trying to do the log timing prediction. The third finding, when we use the item stem, it contained more information related to predicting response time than the response options. So looking at the information contained in the key and its distractors did not provide as rich information as understanding what would be used for timing. And this just kind of is intuitive as what you might think. This is just a comparison here to support that finding as well. And it shows the small differences between the Elmo type that we're using, so the size of the model and whether or not we're able to use some tuning or we had to freeze the parameters, and then whether or not we use the embedding or the encoding for the features. And as you see here, we're a little bit further away in the middle tuning areas. Seem to work a little bit better here. And this just shows the reduction in the RMSE from the original Elmo model versus some of the other models where we use some of the more complex features or embeddings. It's the same result here. The previous slide here, this is for predicting item difficulty, and this slide is for predicting item time. So the three conclusions that we came away here, the transfer learning method 2 works better for pre-value detection, but transfer learning method 1 works better for the prediction and response time. And we think this is really related to the distribution of those variables themselves in our data set. Using the deep learning method for the value prediction was good because we have this very skewed data set, but the normal method of the kind of more simplified version, the transfer learning 1, was great for the response time because when you use a log timing there, it seems to be somewhat normally distributed with just a slight few outliers here. The timing prediction requires more abstract information than the p-value prediction. That is, in order for us to make better predictions on the timing, we had to use the full item stem in order to pull out some of those deep natural language processing features there to understand how to predict that better. And the item stem contained more information related to the item time characteristics than the key and the distractors themselves. There was a limitation here. Could a medical text corpus used to train the models and extracting the embeddings codings, would that work better? We used word2vec and some of the other more commonly used corpuses here that's used in natural language processing. If we had more processing power and we could modify some of the encoding and dense layers, that might be able to get better results as well here. And some other methods here. You'll have to follow up with Kane to get the full import of everything that he had done. There we go. And that's the end of Kane's presentation.
Thank you, Chris, and thank you, Kang, for preparing this great presentation. Again, I don't see any questions in the chat yet. Please be aware Kang is in the chat and he's ready to respond to your questions. I do have one question, Chris and Kang. When you talk about that you need more abstract information in order to predict the timing for the items, what exactly do you mean with abstract information? Can you elaborate a little bit on this?
I can take a good shot. No, go ahead, King. Yes, yeah, I'll let King do better than that.
Can you hear me right now?
Yes, that's much more clear. Yeah, go ahead.
Okay, great. Okay, yeah. So I think that abstract information is that the topic of a piece of document, like the knowledge that the item stem is, related to, and something like that. It means the abstract information like that. So in the traditional traditional natural language process occurred in documents, but in the deep learning we could extract more abstractive such kind of the topic, the knowledge of the piece of documents related to. So it will describe the for example, in this case, the item more accurate than the traditional NLP method.
And do you think your modeling approach could in the future be somehow combined with other methods from natural language processing to improve the model accuracy, especially for long text items?
Yeah, but the problem is that currently we are using a general dictionary of the NLP, But in the future, if we can have specific library which related to the medical knowledge, so it will describe the item or the piece of documents more accurate than the current model.
Okay, great, thank you. So Chris just posted a link in the chat leading to more information on Kang's work. So if you're interested, please visit the link and visit the website. Thank you very much again, Kang. Thank you very much, Chris. And we move on to the next presentation.
Good morning, everyone. Thank you for attending our session this morning. I'm Sue with MBME, and today I'm going to talk to you about estimating spoken English proficiency using automatic speech recognition technology. So what is automatic speech recognition? Simply put, ASR is the process of converting speech into text. As I'm sure you're all aware, personal voice assistants such as Amazon's Alexa or Apple's Siri have gained significant popularity recently. And ASR is actually the first step in enabling these voice technologies to respond when we say things like, Siri, what's it like outside? Automatic speech recognition is also used in assessment of speaking ability. Before the ASR and NLP, natural language processing, NLP technologies have evolved to where they are today, speaking ability was generally measured or assessed using direct observation, and then the scoring was done manually by the raters. But with the developments, especially within the past decade, in the ASR and NLP areas, we can now evaluate speech in brand new ways. These systems leveraging ASR and natural language processing are fast. They are automated, so scores are available instantaneously. They're efficient. There's no need for costly and time-consuming rater training or monitoring. They're transparent, they're consistent, and they're accurate. And we also know that successful applications of these technologies do exist, such as TOEFL's Practice Online. In summary, these factors made us think that Step 2 CS examinations, subcomponents, spoken English proficiency, may also benefit from this technology. Let me give you a little background on the examination. As Peter mentioned before, USMLE, United States Medical Licensing Examination, is a 3-step examination for medical licensure in the United States. It is sponsored by the Federation of State Medical Boards, FSMB, and the National Board of Medical Examiners, MBME. Step 2 CS, second step of these 3-step series, is, I should mention right now that it's currently suspended due to COVID-19 outbreak, but we are capitalizing on this break to see what improvements we can introduce for this exam for its next generation version. So going back to Step 2 CS, it used standardized patients who are actors trained to portray a particular medical case to evaluate medical students and graduates on their ability to gather information from patients, perform physical examinations on the patient, and communicate their findings to patients as well as their colleagues. The exam structure involved 8 hours of testing and 12 SP, standardized patient encounters, where the examinees were told to treat each standardized patient as they would a real patient. And examinees had a 15-minute encounter with the SP. They took the patient history and performed physical examination on the standardized patient. And then they left the room and wrote their they had 10 minutes to write their post-encounter patient note. USMLE Step 2 clinical skills examination had two subcomponents. The first one was communication and interpersonal skills. The standardized patients used a checklist of observable verbal and nonverbal behaviors. Second component was the spoken English proficiency. Again, standardized patients evaluated using global rating scale. And the integrated clinical encounter. Standardized patients used a physical examination checklist to evaluate examinees, and then the patient notes were using a rubric rated by trained physician raters. Our focus today here is the spoken English proficiency. As I mentioned before, the exam is suspended, but we do believe that it is important to continue this work, even though this work started before the suspension, to inform the next generation clinical skills examination, and it is in the works. Let me talk a little about the SEP subcomponent, spoken English proficiency. So SEP performances were evaluated, as I said, by the standardized patients following a 15-minute encounter. They used a rating scale to assess examinees' clarity of communication, which involved things like their pronunciation, their word choice, and need to repeat what they said, and so forth. As you can imagine in this scenario, quality of the information we obtained is very constrained by not only the nature of the instrument, but also the standardized patient's training and their cognitive load. ASR technology is potentially could address both of these shortcomings. First, it can capture and evaluate more nuanced and complex facets of speaking proficiency, such as fluency, grammar, vocabulary, delivery, and etc. And second, it could potentially reduce the cognitive demand by taking over the evaluation of spoken English proficiency. And then in turn, it could improve the standardized patient's portrayal accuracy. So our study's focus was the SEP component. Our objective was to determine if the automatic speech recognition could be used to evaluate spoken English proficiency. And the benefits would include expanding the breadth, depth, and accuracy of the information we captured during the patient encounters, as well as decreasing the cognitive load of standardized patients. So how did we do this? We examined 193 standardized patient encounters. Each encounter was rated 3 times, once by the original rating by the standardized patients, and twice by the experts who were the trainers of SPs on the spoken English proficiency component. We also calculated the average confidence score for each encounter. So what are confidence scores? Let me talk about that a little bit. Confidence scores are essentially the reliability of ASR's recognition. As you might imagine, perfect recognition from ASR is unlikely. The actual recognized speech will sometimes be inaccurate. Just think about how many times you have to repeat yourself with Siri. Confidence scores here estimate the reliability of recognition, and then the systems can use this information to detect and recover from recognition errors. The essential idea is that a voice assistant like Siri needs to understand, needs to know how confident it is about a recognition before executing a command the user is asking. If the confidence scores are low, then it makes sense to initiate an additional confirmation dialogue before executing a command. So we had 2 research questions. First one was, are the confidence scores related to examinees' fluency, clarity of communication, meaning their SEP score? And if so, the second question was, how does it compare to the strength of relationship between human ratings? Here are some results. The first group of bars on the left show the relationship between confidence scores and human ratings. E1 is the expert rater, E2 is the expert rater 2, SEP is the original rating assigned by the SP, C is the confidence score. And the second group of bars on the right display the relationship among human raters' ratings. All the relationships we observed were in the expected direction here. The highest correlation we observed was between the two expert human raters, which is also expected. On average, humans' agreement was 0.1 higher than the agreement between the computer and the human raters. However, they are impressively close to the human agreement. In other words, we could potentially use ASR confidence scores as reliable estimates of traditional SEP scores. So what are our next steps? Our next steps involve expanding the current study using a larger sample and more cases. Current study looked at 19 cases. Number 2, obtaining better audio. The quality of audio files used in this study were not ideal, far from ideal. We know that from our pilot studies, we can get a much more accurate ASR results when we use individual microphones like lavalier microphones, rather than using a single ceiling microphone, which is what was used in this study. In fact, in this study, the audio quality may have disadvantaged the confidence scores. We don't know by how much. Number 3, we could use NLP and ASR technologies to evaluate more nuanced and complex facets of the spoken English proficiency constructs, such as grammar, vocabulary, and delivery, and so forth. And finally, we can extend the use of this technology to assess communication skills, which was a part of the previous version of the clinical skills examination, and which is also very likely to be part of the next generation clinical skills examination. Thank you very much for your attention. Please email me if you don't catch me with the chat today. Email me with any questions.
Thank you so much, Sue. Again, I do not see any questions in the chat yet. And since we talked about it yesterday a little bit, could you maybe elaborate on what types of adjustments you needed to implement in the system that you used in order to allow to apply to the given item pool that you worked with?
What sort of adjustments, meaning?
Because you had like specific items, so you probably expected a specific type of text or conversation. Is this something that you accounted for in any way to make it more feasible for the system to?
That's right. So we would have to expand the item pool, meaning the case pool that we used. Current study used 19 of a very large case pool. So as you can imagine, the corpora or the text was very limited in this study. So by extending it to a larger sample of cases, we can get a better sense of how successful this would be. And also the microphone.
Mm-hmm. And how, or do you have any, did you explore how easy or difficult it was for the system to handle different people from, you know, who are not English speakers, who come from different languages?
That study is in the works, actually. That's we're working on that right now, but we haven't. That's a great question.
Because that, I guess that's something that can be become very complex very quickly if you have all these different
accents, very
pronunciation
true.
And accents.
It's a big problem for the ASR systems.
Mm-hmm.
Very true.
So we have a question from Sergio. How much variability there was in the microphones used? Were provided by the examinees, or it was standard in some way?
The microphones were standard. The encounters were taped at the clinical skills examination centers. We had 6 of these centers across the country, And all the microphones were standardized across each room for each encounter.
Okay, so I do not see any other questions in the chat. If you have any more questions, please feel free to email Sue. And thank you very much again. And on to the next presentation.
Thank you.
Is it okay to start, Lale?
Yes, it is.
Okay. Good morning. I'm Janet B, and I'm here to talk with you about identifying response patterns in clinical notes with NLP feature identification. I'd like to thank my teammates, Ravi, Drew, and Chris for all their work on this with me. The purpose of the study here that I'm going to talk about is how we can evaluate NLP features extracted from constructed responses, and we can use them to look for patterns to inform test development and provide feedback to test takers. The data that is used in this study is from the patient note from the USMLE Step 2 CS exam that Sue just described in her presentation. But instead of focusing on spoken English proficiency, we're going to take a look at the patient note. And this is the note that is completed after each test taker interacts with the standardized patient. You can see there are free text areas for the history and physical exam, and those two elements are usually scored together. And then there are there's boxes at the bottom for diagnoses and diagnostic studies. These sections are rated by trained physician raters, and they use a 1 to 9 score scale. Part of that scoring is based on the presence of key features in the patient note, and those key features are important pieces of information that the test taker should have gathered or written down as a diagnosis in their patient note. So just as an example for a patient note, this is a sample from a history section where the test taker wrote about a 58-year-old female with a history of jaw pain and bruising, and continues on. The key features for this case would be pain in the jaw, that it happened last week, that it hurts to chew. And so a human reader, when reading this, would be looking for the presence of these key features and use that information in calculating a score. NBME has an NLP engine that can go through and identify pieces of text that correspond with each of the key features. What this provides us is basically a checklist that says, for this test taker's patient note, the following key features were found. And since this is an NLP engine, it's a nice piece of software that can do things over and over again, and we can do this for lots of test takers. And we convert these check marks to 1s and 0s, and we have a lovely data frame that in the measurement community, we have a large arsenal of tools for analyzing. But we're not the only field that has data that looks like this, a bunch of 1s and 0s with row headings and column headings. And I'm actually going to turn to the world of grocery stores and borrow some of their data mining techniques to see, if that can be useful for us. It's easy to imagine that a grocery store might have data that looks like this. They don't have NLP features or key features. They have shopping items, and they don't have test takers. They just have regular shoppers. But their data looks like ours. And some of the questions that grocery stores owners tend to ask is, what groceries are bought together? They try to look for frequently paired items. And in the same way, we can look at what features are found together. And what might this information help us do? Well, we could look to see if the features are performing as we would expect them to do. We can also look at the way the features group together in ways to see if they follow cognitive theories or lines of inquiry. We can also look at the feature groupings for different subgroups to do kind of a diff analysis. And finally, we can look at the different feature groupings for standardized patients as a form of quality control. So it looks like looking for frequent patterns could provide some information, and we can borrow some tools from the grocery store data mining toolbox. One of the tools we can borrow is the binary similarity measure. This is calculated based on the crosstabs, and we could go through some rigmarole with equations, but it's really just the proportion of times that the two features had the same value. There's a symmetric and asymmetric version. We went with the symmetric one because we assumed that both of our features had the same weight. But really, this is just the number of times that the features had the same values. A second tool that we can borrow from our grocery store friends is the market basket analysis. In market basket analysis, grocers look for frequent item sets, what items are typically bought together, and those item sets are called rules. So examples of rules that you may see in your shopping cart: cookies and milk, cheese and crackers, beer and diapers. You might want to look that one up if you're interested. It's more of an urban legend, but it's a cute story. So how do you get these rules? Right? What's the process for developing these rules? The answer is a priori association rule mining. This is a way to mine data sets for frequent and interesting patterns. And there's a couple words here that should probably be unpacked. The a priori refers to the condition that an item cannot be part of a frequent item set if that item itself does not occur frequently. So an individual item occurring frequently is kind of the requirement for entering into the possibility of being in a frequent item set. This is why cookies and milk is a frequent item set and cookies and sardines is not a frequent item set. And the concept of frequent and interesting also needs some definition. Frequency is usually defined through two terms called support and confidence. Support is the frequency with which the two features or the items in the item set appear in the data set. This is a parameter that is set by the researcher as kind of the minimum threshold. Confidence looks at how frequently one feature appears when the other feature is present. This is a conditional probability, and together, support and confidence act as gatekeepers for limiting the size of the rules that are returned. As you'll see in a little bit, you can get a lot of rules returned from rule mining. Interestingness can be examined through many, many different indices. I just selected lift as an example of one of the interestingness measures. Lift is probably the most commonly used one, and it really gives us information of how much better this rule is than just a random model. And so we'll see a little bit about that later. For those who are interested, here are the equations that go with support, confidence, and lift. Before going any further, I'd like to stop and regroup because I've gone over a lot in about 5 minutes. We've talked about how we have a clinical skills exam that has a patient note associated with it. We have an NLP engine that processes the patient notes, looking for the presence of key features, resulting in a lovely data matrix full of ones and zeros. And we're borrowing some tools from our grocery store data mining toolbox and going to look at the data with respect to binary similarity measures and do some association rule mining. The data that we're using comes from Step 2 CS exam, and we selected 10 cases. So on this chart, on the vertical y-axis, we have the number of features that are found in each case. Along the horizontal x-axis, we have the number of patient notes. Each case had a minimum number of 1,500 notes. due to security concerns. That's pretty much all I can tell you about our sample size here. And you can see the cases are a variety of different clinical complaints, patient ages, and gender. Taking a look at the symmetric binary similarity measures, I just selected 3 cases actually randomly to show you. As you're looking at the different plots, the HX that you see in the variable names off to the left, those stand for the history items, and the letters PE stand for physical exam. And you can see there's some different interesting patterns, but what you see in each of them is that HX1 and HX2 are usually very similar. I have shown these plots to different people and everyone has asked the same question, so I'm just going to assume that some of you might have it and answer it in advance. How does the symmetric binary similarity coefficient compare with a Pearson correlation coefficient? And you can see that they really do provide some different information, which makes sense because the binary similarity coefficient is really just the proportion of agreeing pairs, and the Pearson correlation coefficient is based on variance. So you do get different information. Going to step over now and take a look at the resulting rules from case 2. I again just selected a case. This one had the smallest number of features. This had only 10 features in total and resulted with not a lot of rules. These rules were generated with a minimum support threshold of 0.6 and a minimum confidence threshold of 0.8. You can see that most of the rules include HX1 and HX2, those first 2 history items, which were very similar in the previous plots that we looked at. This table does show the support and confidence for each rule, as well as the lift, leverage, and conviction. And the lift is really showing us here that these rules aren't getting us a lot, but they are interesting to look at and really require content experts to review them and see how useful they can be. What was interesting is the number of rules that was returned for each case. Again, we have the number of features along the x-axis and the number, along the y-axis, and the number of patient notes along the x-axis. And if you look in the upper right-hand corner, you can see that we have a lot of variation in the number of rules returned for cases that have a similar number of features and similar number of patient notes. So in summary, compared with holistic scores for clinical notes, the identification of key features provides us with some interesting perspectives. We can borrow some data mining tools from other areas, such as the association rule mining, to find frequent and interesting patterns. And we compare those patterns with content experts to review case content and how the individual features may be functioning. Thank you for your attention, and please contact me with any questions.
Thank you so much, Janet. It was very, very interesting. I don't see a question in the chat yet. Janet, what do you have any next plans with this study or any extensions that you're going to look into in the near future?
Yes, so number one, bringing some content experts, but also association rule mining is really entry-level rule mining. There are many different algorithms out there, and one next step is also looking at this with respect to network analysis. A heterogeneous network analysis is usually paired with association rule mining. So that should also provide us with different perspectives.
Okay, great. That sounds super interesting. We're looking forward to the next results that you're going to present. So I think we can move on to our last presentation from Chris.
There we go. Sorry. Great. Again, my name is Christopher Runyon, and this afternoon I'm going to talk to you about an automated scoring routine for constructed responses on a medical licensure exam. So the constructed response that I'm going to be talking about is the patient note that is written during the Step 2 CS examination. And this is the examination that both Sue and Janet have been talking about in their presentations. The patient note here is part of the clinical encounter. So for the presentation, it's important to note that the patient note has two sections, a data gathering section and a data interpretation section. The physician raters provide independent scores on each of these sections. So each patient note is going to have a data gathering score, and each patient note will have a data interpretation score. And as you'll see, the structure of the information in these two sections is quite different. And as such, it was necessary to develop independent computer scoring or computer assisted scoring programs for each section. We all know that using human raters has some potential issues. It's expensive. You need to train the raters, and you have to pay the raters for their time to score the notes. Two, it can be slow. Often these raters have other jobs, such as being a doctor or working in some medical educational profession. So they need to do this in their spare time. And then that also adds time to us getting back to the students their scores. So it delays score reporting. And then there's just going to be some natural variability across ratings. So depending on who saw your note, your average score. So it's possible the score you receive on the note depends on which rater sees the note itself. So with these issues in mind, we want to develop a computer assisted scoring program that would reduce these problems. We could quickly and cheaply assign a score to an examinee, and it would eliminate the variability in scores for very similar notes. So this is the top portion of the patient note here. It's the data gathering portion of the note. The first half of the data gathering section is on the patient history. In this section, the examinee is going to document pertinent information that was extracted from the standardized patient through conversation. This is going to be information like what are the presenting problems that brought you to the doctor. They're going to document information that was relevant to the patient's lifestyle and its habits, maybe some family history of some similar types of illnesses here. So that's going to be all written in the patient history. Then just below that is the physical examination section. And that's where the examinee is going to report any findings from physical examinations that they actually did on the standardized patient. This would be listening to the heart or lungs for any abnormalities, seeing if there's tenderness in the lower left quadrant when they press on it, just some things like that. So examinees are going to enter text in these two sections of the patient note. This is done through a computer interface when they're actually in the exam. This patient note is then processed through the natural language processing system that Janet had mentioned. It's a concept detection system to see whether or not concepts are absent or present in the note. And then we get an output that looks something like this. This is going to look very familiar. This is pulled directly from Janet Mee's slide, who presented right before me. This is a great visual because it leads directly in how we're going to develop the model for the data gathering scoring section of the patient note. So what we see here, just to refresh your memory, is we can see what concepts were detected by the NLP program for the different examinees. So the first two examinees here, 1 and 2, had most of the concepts were detected in their patient notes, whereas these examinees 3 and 4, not as many patient notes were, or not as many concepts were detected in their notes. This is a more accurate representation of what the data looks like coming out of the NLP engine, or to be more precise, it's transposed and it looks like this. So what we have here is each row is a vector for what concepts were or were not detected in that patient note. So for here, for patient 1, you can see what concepts were detected here. And I've just generalized the features here to be specific to any type of patient note here. So we have a vector of 1 through K features for any examinee. Now, as you can imagine, we've been running this exam for several years. So we have several thousand patient notes that have been seen and scored by physician raters. So we can put those previous patient notes through the NLP program. We can get out these vectors to see what concepts were and were not detected. And then we can pair that with their actual equated human ratings that the examinees receive for those sections there. So from here, we just use linear regression to obtain estimates of the relative importance of each of the key essentials. So then you can input a new unscored patient note and apply normal regression prediction methods to arrive at a score for the examinee. There's a starting value that's given to each examinee that's case specific, and then each of these coefficient values are case specific as well, as you would imagine. So for examinee 3, you'd be given some sort of starting value that'd be relevant to the case. Because concept 1 was detected, you would add 0.46 to that starting value. Because concept 3 was detected, you would add 0.37 to that starting value, and so on, and you would come to a number that would be very close to 5.62. So as I mentioned, we use linear regression, but there's two reasons why we use this. One is it needed to be legally defensible. The executive committee was concerned, and rightly so, about ensuring that we had a scoring system that was transparent and pretty easy to explain to non-statistician or non-measurement people. If we were going to use a more black box approach or a more opaque method, that was thought to be problematic. And two, fortunately, linear regression worked as well as other predictive modeling approaches that we explored. Here, I mean, as well as means either not significantly worse or actually significantly better than the majority of these methods. If one of these methods had worked better consistently across all the cases, then my next job was going to be figuring out how to explain that method in plain language and then explaining that to the majority stakeholders. But fortunately, it didn't come to that. And that's how we score the DGE, that top portion of the note there. Here is the data interpretation portion of the note. As you can see, it's structured quite differently here. There's a space for the examinee to enter a diagnosis, and then they're to enter supporting information for that diagnosis here that comes from the data gathering section. So when you say that you think that I have some sort of heart problem, you're going to need to give me some information from the histories that document and support why you believe that diagnosis is going to be correct. There's two important instructions that are kind of blurry up here that I definitely want to bring your attention to. List diagnoses from most to least likely, and list up to 3 diagnoses. For some cases, fewer than 3 diagnoses will be appropriate. So thus, there is meaning to the order in which the diagnoses are presented, and there's a variable amount of diagnoses that are appropriate for each case. For each diagnosis, there are 3 possible categories that can be that diagnosis can be put into. 1, this is an expected diagnosis. This is the diagnosis that is listed on the case blueprint. The key essentials in the case are designed with this specific diagnosis in mind. 2, there could be a plausible diagnosis. This is a diagnosis that is somewhat reasonable to assume given some of the key essentials. It's not exactly what was expected, but there is some value to that diagnosis. And then 3, there's an implausible diagnosis, that the diagnosis doesn't follow from the information that's to be extracted from the case. The expected diagnoses themselves can be further broken down. So let's take a case with 3 expected diagnoses as an example. The diagnoses could be unordered, meaning that the 3 diagnoses could be presented in any order and are interchangeable from a scoring standpoint. So it didn't matter what you put in diagnosis position 1, diagnosis position 2, or diagnosis position 3. You could switch those all around and it would be scored equivalently. Or there could be an order to the diagnosis. It could be that there was a lead diagnosis that should be listed first, and then the other 2 diagnoses are just expected and could be listed interchangeably. Or it could be that there was a fixed order to the diagnoses where there is a specific lead diagnosis, then a secondary diagnosis, and a third diagnosis. So when raters score the DI section of the patient note, there's a scoring rubric that they use with specific point deductions for specific errors. The examples I have here are just intuitive. I'm sure you all can think of them yourselves. If you didn't include an expected diagnosis, there's going to be a deduction for that. If you had an implausible diagnosis, you're going to have a deduction for that. If you were to list a plausible diagnosis prior to an expected diagnosis, it's an order error because you're supposed to list the diagnoses in order of their importance or their relevance to the case. There could even be combinations of these. You could list an implausible diagnosis prior to an expected diagnosis, and there you're going to get dinged twice because there's an order error and you've included an implausible diagnosis. Let's look at a couple response patterns in order to better understand how that information is structured. So this example case I'm going to be using is a 3 diagnosis case with 1 lead diagnosis. So examinee 1 that we have here has answered as we expected or what we would hope. They've demonstrated they're proficient in this area. They've listed the lead diagnosis first with the 2 expected diagnoses afterwards. The second examinee here, they've listed an expected prior to the lead. So we'd expect there to be some sort of deduction given there by the rater. And they also have failed to list the other expected diagnosis here in the 3rd position. So there would also be a penalty. And here's something that we found in our work that came out. As you can see for examinee 3, they have 3 expected diagnoses. Well, the case only has 2. So what happened? Well, as frequently may happen as an exam, an examinee want to include as many diagnoses as possible to cover all their bases to make sure they get credit for the item, or as much credit as they possibly can for the item. And when they do so, they'll enter a diagnosis that is similar or equivalent to something else that's been already entered from the scoring standpoint. The wording may be slightly different. They may emphasize an emphasis on one part of the diagnosis over the other. Like I said, from the scoring standpoint, they're deemed to be equivalent. So thus, we not only needed to capture the order and the category of the diagnosis that was entered, but the number of unique valid diagnoses from the case. And this lets us summarize all that information in this nice 4-character pattern here. The 3 letters correspond to the diagnosis category and their position, and the single number at the end corresponds to the number of unique valid cases or diagnoses that were given in that case. So we have some very specific scoring rules that need to be accounted for, and we also need to account for when an examinee enters a synonymous or repeat diagnosis. How can we account for all this complexity? We trust our human raters. The human raters follow all these guidelines when they're deriving a score for the data interpretation portion of the case. So we can rely on our raters to guide the computer-assisted scoring system. In a sense, when a human rater sees this information that I've presented over here in the table, all of these scoring complexities are already baked into the score that they give the case. So once we have this response pattern here, this 4-character string that shows the category of the diagnosis, the position of the diagnosis, and the number of unique valid diagnoses, that's all the information that we need to assign the examinee a score for the data interpretation portion of the exam. So the score assigned for each examinee is the average rating for an examinee with that response pattern. So to hop back real quick, what we do is we take all examinees that fall into pattern LEE3 for this specific case, and then we take all the scores that the human raters gave that examinee, and we give the new examinee that's going to have that same pattern the average of all of those scores, and so on for each of the score patterns. It's equivalent to regressing the rater score on all 3 diagnosis categories, the number of unique valid diagnoses, and all possible multi-way interactions. So this first equation that I have listed here is the R shorthand for those of you that like to use R for data analysis as well. I've tried to write out the full equation here at the bottom. I may have made a mistake, but you generally get the idea. It's all of those predictors and all of their possible interactions. All right, so I've left a lot out of this, but I wanted to make sure I gave you all a general feel for how the computer-assisted scoring program works. Some of the things I didn't cover were talking about tuning insight. That's the NLP concept detection that Janet and I have mentioned there. A lot of work going into making sure that we can use a computer-assisted scoring program is that ensuring insight is working well. So it took a lot of work for us to do. How to incorporate the support information for the diagnosis. I completely glossed over that and skimmed over that for this presentation here. How do we select our training sample? As you can imagine, we think some raters are doing a little better job than others when they're providing some scores. So how do we figure out what we want to use as our training sample and as the basis for the program, and lots of other things here. I'm currently working on a pair of manuscripts, one that talks about the scoring and the other one that talks about diagnosing the quality of a case before you promote it to operational work. So please reach out to me with any questions that you have, or you can wait for those manuscripts to hopefully be published here in the next couple of months. And that concludes my presentation.
Thank you very much, Chris. I don't see any questions in the chat room yet. Chris, I was wondering, so what you have presented so far is that you use the computer-assisted scoring system in order to support the human raters, more or less, to a certain extent. Is there, or you also use the human raters to support the coding system, the automated coding system, so vice versa. Is there any plan, or do you see any possibility based on the methods that you are allowed to use for this exam, that the scoring system, the automated scoring system, can at some point replace the human raters? Is this something that is wanted? Is it something that you think one should be really cautious about?
I don't think it can ever fully replace the human raters. We do need that in some instances. One of the things that I didn't speak about that was important is we identified some sort of conditions where we didn't feel comfortable giving the note a rating. Like I said, we've really worked well to have the insight detection engine work nicely, but still there's some small percentage of notes where some of the diagnoses aren't detected, so they don't know what category it falls into. So we definitely need human raters for that. It's also helpful too, just to make sure to continually calibrate our rating system. So just as a quality control, we send out a certain percentage of our notes just to be reviewed by human raters anyway. So we want to continually update our system and further refine the scoring just to make it more and more precise and valid as possible.
Thank you so much, Chris. And since there are no more questions, I think we can move on to our discussant, Dr. Isaac Behar. Just as a few introduction words, Dr. Behar used to work at the Educational Testing Service, ETS, for many, many years. And besides many other things, he is one of the experts in the area of automated scoring of constructed response formats, learning analytics, and machine learning. So we are really, really excited to have him here as a discussant to discuss the really interesting papers that were just presented. So please, Isaac, feel free to start.
Does that work?
That's great.
Yeah.
Yes.
So first of all, glad to be here. Thank you, Lally, for inviting me to make a few comments. This is really a great opportunity for me to touch base with the NBME world. Back last century, during the 1990s, NBME was developing automated scoring system while ETS at the same time was developing automated scoring systems for architecture. And I remember we had several interesting meetings during those years to touch base on how each of us were approaching the automated scoring. So thank you, Lally, and thank you to the presenters for sending their presentations in time. I will have very brief comments on each and not in the order in which they were presented. The general nature of my comments is what's next, because I find the progress presented here quite exciting, and I want to see what next steps are. But at the same time, I'm also interested in how this innovation that you all are working on interacts with the side of the house that produces the items. If you know some of the work I've done, I've been interested in the question of item difficulty modeling, which sort of brings tries to understand why items are more difficult or easier, and whether the item writers are aware of that and whether they can do anything about it. So those are going to be the nature of my brief comments. So I'm first going to talk about the last two presentations, just to annoy everyone. I'm going to go in reverse order. So this, as we just saw, these two presentations are related. They are concerned with the patient note. By the way, I've been aware of standardized patients for a while. But I've never seen it in action, and I put a link on my slide here. There's a very nice video by NBME on what goes on, and I was very interested in the control that goes into it and how carefully it's all done. I found that very useful to give some context to some of the results that were presented. So, so me and colleagues talked about identifying interesting patterns in this set of binary vectors, whereas Chris was concerned more with the scoring of these things. Obviously, these two things are related, and I didn't see any evidence that there was there were connections being explored between the two sides. I'm sure back in the office, some discussions are going on with respect to that. So, so about the me in colleagues' presentation. I think it was very, very clear. So we have these patterns of 0, 1s, and the question is, are there sub-patterns that are interesting in their own right? And the methodology that was proposed for this was basket analysis, which I must admit is not something I have run across. I think is used for analyzing baskets of groceries, etc. And one thing that the grocery stores do with that is they try to locate the products on the aisles in such a way that not necessarily that it's convenient to complete your shopping, but actually to make you shop for more. So it's an interesting methodology, not something I was aware of. My question is a simple one. Are there more psychometrically oriented methodologies that could be applied here? I could not think of any, but the basket analysis is quite removed from psychometric types of analysis. So I was wondering if there are other more familiar methodologies that could be relevant here. So that's one question. With respect to Chris and company's presentation, I think also this presentation was also perfectly clear what's going on. One misconception I had is that these key features that go with every case, if you get a 1 on each of those, that was the sort of the best response pattern. But I think Chris clarified that that's not the case. Apparently, the highest scoring response pattern can have some zeros in it. I don't quite understand how that works, but in content scoring, the idea is there's certain concepts that the student needs to mention, and the more that you mention, the higher your score. This obviously is a very different situation here. One question, I guess the main question I have for Chris is what happens when there's a new case? In other words, obviously the approach to scoring taken here is very empirical. It means there must be a lot of human scores associated with the different score patterns. And so when a new case comes along, you will have no data. I suppose you could pre-test them to collect the data, but I'm curious what happens with new cases. I'm also curious whether the cases have family relationships so that in fact you could, whatever you have learned from one case can be applied to other cases. Again, these are questions out of my ignorance as to what goes on with this type of test. Moving on to the next question. This I saw all the presentations were technologically and methodologically first rate, but obviously this one pushed the envelope in the sense that it brought into a psychometric context some of the machine learning methods, including word vectors, which we have used those in sort of verbal analysis, verbal type tests to understand difficulty. So this goes beyond that. It applies some of the latest word embedding approaches. One comment on the application of machine learning is that I think the presentation mentioned that there were 18,000 items, and we do know that machine learning requires these huge samples to create these models that have sometimes thousands of parameters. So my general comment on this is whether there is a less demanding approach to effectively redo this analysis. And one example of a less demanding approach, which goes, however, beyond linear regression, is this idea of gradient boosting machine. And I mention it because we have used it ourselves successfully, I think, to predict the difficulty of items, in the sense that when we apply that compared to the linear regression, the R-square increases by quite a nice amount. So my question for these presenters is whether something simpler could work as well, and in connection with the fact that you may not always have 18,000 items. Sometimes you may have hundreds of items, which is the situation we found ourselves in when we applied GBM. And in that context, GBM we thought worked pretty well. Sue also presented a very technologically exciting study. It was quite clear. I guess one question I had, knowing what had to be done in TOEFL, early on at least, I'm not sure what it's been on lately, but early on I know the adaptation of the ASR, the automated speech recognizer, to the speakers and to the context was very useful in improving the word error rate. So what was done in that context would be useful to know. With respect to ambient noise, this is a real problem. It's also a problem in TOEFL, where you have a test center and other students are talking at the same time. My understanding is that there are some AI developed noise cancellation systems that are being considered or already in use. In fact, I installed one of those on this laptop, something that NVIDIA gives out for free. I hope I'm coming across clearly, because I could hear everybody quite nicely. The other comment on Sue's presentation is the issue of accented speech. In that video I mentioned at the beginning, I noticed, not surprisingly, there were many foreign students taking this test. And what is the situation there? Could be interesting. This could have implications for diff. I can tell you, I've been a consumer of this technology for a while, and I'm quite amazed that the recognizer that Google uses, or whatever is in my phone, recognizes me completely. It is quite impressive. It wasn't the case all along. Earlier on, it was pointless to use it, but now it's really like dictating has become quite visible. Finally, on to Peter's, the first presentation. Again, this presentation is sort of music to my ears, in the sense that it's a form of automated item generation, or you could call it a human assistant item generation. So it is a very it's a very nice application that there were not example of items, so I don't know what these things look like. But in a vocabulary type item, like you have on GRE and things, this would be akin to suggesting to the test developer to use certain words as distractors. So this is very, very reasonable application. When this work is further along, I would be interested in knowing what reductions in time there are on the part of the item writer. For many years, we try to get TOEFL to do item generation of vocabulary items. But what they said was that, hey, those are the easy items. We don't need any help with those. Those we can crank out very quickly. So it would be interesting to know in practice how useful this idea of suggesting distractors is. And then once this is implemented, I would be interested in knowing if there's any reduction in the discrimination of the item, perhaps substituting distractors that were useful in another item. When you force them to be in another item, I realize the test developer is exercising judgment as to what gets put there. But the possibility that the item suffers in discrimination from this approach to doing distractors is possible. So I would, like with the other presentations, I would be interested in knowing what the next steps in this line of work are. So those are my comments. Thank you very much.
Thank you so much, Isaac. That was really, really helpful and interesting. I know we have reached our time limit for this session, but I would really like to provide each presenter with at least a minute to be able to respond to Isaac's questions and react to his comments, especially for the recording. So please go ahead. Maybe we can start with Peter.
Thank you. Thanks, Isaac. Yeah, I mean, I agree with everything you said. We haven't tried it out with actual item writers, so who knows what's going to happen. And we certainly don't have any items that were generated through this process yet, so we don't know how this process is going to affect them. It's something that's been on our mind. For example, over time, it might affect our item pool. We might get fewer and fewer, less and less variation in distractors within our item bank over time through a process like this. So that's something that we're a little wary about. And as I mentioned in a slide and that you commented on, the computer does much better at things that aren't that difficult. Coming up with the really good, difficult distractors for very complex items is something that the computer doesn't do as well as coming up with the things that aren't that difficult to come up with. So we had quite a few item writers comment that some of the suggestions were fine distractors, they just didn't need any help coming up with them. So, you know, that's something that we're gonna have to struggle with moving forward. Anyway, again, thank you very much for your comments.
Thank you, Peter. Sue, would you like to react to Isaac's comments and questions?
Yes, I would. Thank you, Isaac. Those were very thoughtful comments. I want to agree with you on both of your comments that number one, you're absolutely right about 35 to 40% of our examinees are indeed English as a second language examinees. So it is very relevant. Your comments are very relevant to this current study. And another study is under works that we're looking at. We're comparing English as a first language and a second language examinees and how we can recover their speech, how successfully we can recover their speech in this context. So hopefully next year I will be able to talk about that. And the second one, word error rate, is absolutely, I would have loved to present that with this study. It just turned out to be an incredibly time-consuming and computationally heavy task to do in time for this conference, but we are definitely going to be including it. Thank you very much again.
Thank you, Sue. Janet, would you like to go next?
Sure. Isaac, your comments pretty much aligned with my to-do list. So whether or not you were actually had seen that to-do list, but it was a good nagging of things I need to get working on. Many clinical skills exams are scored with checklists. In fact, the Canadians do a lot with checklists. And it aligns nicely with the whole key features assessment model that happens in medical education, especially with clinical skills assessment. And so there are a whole repertoire and kind of standard measurement models and procedures for evaluating checklists. And we can liken the NLP features that we get as kind of functioning as a checklist. So I appreciate the nudge of things that I need to get working on.
Thank you, Janet. Chris, would you like to respond to Isaac's question?
Yes, I would. So thank you again, Isaac. Yeah, that's the coming up with new, or what do we do in the case of a new case is something I didn't get to cover. The routines that you see in the programs that we developed for the automated scoring were developed after the data was handed to us. So the cases were already created, the data had already been collected, and they were proceeding with the exam as they usually had. So this was something we had to develop on top of what was already happening. But now with the pause in the development of new cases, we're excited because we can kind of bake in some of these important information that we want to extract through the NLP concept detection engine there. So we can work with the case creators in order to make a case a little bit better aligned to using the automated scoring system. And then, like you said, we're gonna have to always use human raters. So we've piloted and we've looked at when a certain case goes live, how many cases are gonna need to be run. And it's not so much that we need a large number of cases in order to feel confident in the automated scoring, but as long as we see a nice distribution of case scores that we usually see within the population we can see. So that's the idea is all the cases also need to go through a first term in order to be able to be equated in the larger system of, you know, the equating the across cases into there. So with just the normal time frame that we use, you're correct, we're not going to be able to use the auto scoring for the first round or two of cases. And during that time, we'll just collect all the human ratings, and then we can use that and just put it into the system. And then from there on out, we continually, we can use the automated ratings. And like I said before too, a portion of the notes are always scored by humans, so we can continually improve what the points are given for the different DG sections and fine tuning what the DI section score should be there as well. And we're also looking to incorporating some other information like you had mentioned, just have to do with other linguistic features of the note besides just the context defect detection system there to see if we can further improve the DG scores.
Thank you, Chris. Ken, do you want to say anything? Is Ken still on the line, maybe? Or it could be that he has some connection issues. Ken, if you're trying to say something, you are muted.
Yeah.
I think we cannot hear you, Ken, unfortunately. Do you want to write a response in the chat, maybe? I'm so sorry, Kang. I'm afraid we cannot understand you. And it looks like we have to end the session in the next few minutes. So I will allow Kang maybe to discuss his point with Isaac maybe after the session, per email or in a private discussion. I'm so sorry. We do have to end the session. We would like to thank the authors for sharing their valuable research and the discussant for the great discussion of the papers and the helpful feedback and the new insights. I believe this was a great selection of studies which utilized data from really complex item formats to support not only the data analysis, but also advance the scoring interpretation and test development.
Is that okay right now?
Sorry, Kang, we are ending the session. We would also like to thank the audience for participating and for their interesting questions. Enjoy the rest of your day and the ongoing virtual NCME conference, and we hope to see you in person next time. Thank you and goodbye.